Alright, look. This isn't so bad. We get to do this in the comfort of our own homes. We get to do math where we can wear slippers and sweatpants and eat ice cream. I have dogs. I could be doing math with dogs. It's better than doing math without dogs. We're going to be fine. And we got it. Because, baby, it's cold inside. One, yes, I did get a haircut. Thank you. Aw, thanks. And two, just because we're doing this virtually doesn't mean that you get out of the classic question, what did we do last time? You take a minute, think about it, write it down, don't use your notes, and I'm going to go see if we have any ice cream. Great news. Ben & Jerry's tiramisu, which I don't know that I've ever had. We're gonna find out if it's any good. Espresso fudge chunks. That should get us through this video. I just gotta find out how to get this open. I should probably do that off camera so that I can save face a little bit. Hey, what did we do last time? Let me tell you. Last time we introduced this idea of a Riemann sum, which is our way of finding the area under the curve of a function, or approximating it at least. Here in our example we were looking at this function, f of x equals x squared plus 1, and we were looking between 0 and 4, trying to find the area underneath this curve. But our definition of a Riemann sum was to find a bunch of rectangles and put them underneath the curve and add up the area of those. So we started by breaking the interval up into some subintervals, starting with 4 subintervals and going from there, and saying, well, how long is each one of those going to be? When n equals 4, the length of my interval from 0 to 4, well, it's going to be 4 minus 0, which is 4. And since I'm breaking it up into 4 subintervals, I'll take that, divide it by 4, and say, well, each one's going to have length 1, and we called that delta x. Now I know where each of my subintervals begins and ends. If I'm going from 0 to 4, and every rectangle has a length of 1, or a width of 1, that I know that I'm going to have a rectangle beginning at 0, beginning at 1, beginning at 2, and beginning at 3, and going through there. From 0 to 1, 1 to 2, 2 to 3, and from 3 to 4. I've broken down that interval into my 4 subintervals. From there, we put in some rectangles that go up to the curve. Of course, we have to decide how we're going to do that, and our options were to either pick the left endpoint of our interval and send that up to the function, see where that hits the curve. We could also just as easily do the right endpoint of the interval, send that up to the curve and see where that hits. We could pick the midpoint of the interval and send that up, which feels kind of nice, a little bit of balance. Or we could just pick a random point in the interval, just throw a dart at it and send that up. It doesn't matter. It still meets the definition of a Riemann sum regardless of what you pick. But for our example, we used the left endpoint and we went from there. So for each one of our intervals, we picked the left endpoint and had our rectangle go up there.
For the first interval, the left endpoint was at 0, so we took f of 0, which is 1. Remember, we're going off of the function that was given to us, f of x equals x squared plus 1. For our second interval, well, that left endpoint was 1. So when I send that through the function, it goes up to 2. The third one goes up to 5, and the fourth one goes up to 10. And we did this for all 4 of our little subintervals, found their area, which is pretty easy to do, base times height, that's why we like rectangles. I know all of their widths, because they're all 1, and we just worked out all of their heights, so that's easy to do. 1 times each of their heights gives me those 4 areas. We added them up, bada bing, bada boom, and 1 plus 2 plus 5 plus 10 gave us 18. A little bit off of the actual area of 25.33, but hey, not bad for 4 rectangles. Our idea from here was to say, well, great, we crank up the rectangles, and you'll crank down the gaps. That's our big problem here, right? We've got all these gaps between my rectangles and the curve, and I want to get rid of those. I want that to become less. More rectangles, smaller gaps. So we tried it again with 8, and well, I kind of just did a lot for you this time because we changed things up a little bit. Instead, the length of my interval is still 4, but now with 8 subintervals, they'll each have a width of 1/2 or 0.5. And we said that in general, this will always be a good process for getting our delta x. I'll just take the length of that interval, b minus a, and divide it up by n, the n subintervals that I need. In the first case, n was 4, so they all had the width of 1. Now that it's 8, they'll all have a width of 1/2. This time we went by the midpoint instead of an endpoint, which made the math a little bit worse. But we made it through for all of the things on our table, sending rectangles up to the midpoint for each one of them, adding up the areas, and getting a whopping total of 25.25, which was a lot better, honestly, but still not quite exact. This whole process was what led us to our official definition, boop, 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 woo, of a Riemann sum. If you didn't do the boop 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 woo with me, you can always rewind the video a little bit and try again. But we got this formal definition of a Riemann sum, which is exactly what we just did. You take all of our rectangles and find their area, which is base times height, and then you add them all up using that summation. However you choose to do it, left endpoint, right endpoint, midpoint, random point, doesn't matter. Even if you have your widths all be different values, that's okay too. It all meets the definition of a Riemann sum. That's where we left off, and that's where we're going to pick up. There's like a chocolate ganache. It's like a hard shell. I can't get into it. I guess it's been in the freezer for a while. Anyway, the place to begin here is where I left off, which was actually a try with a buddy, where I wanted to give you the opportunity to try to find a Riemann sum with a buddy. So if you have a buddy near you who, knows calculus, then great, yeah, wrangle them in, get them part of this. Otherwise, you can have a look at this question on your own for a moment. That's not bad. Here's a try it with a buddy question, aka try it on your own. I'm going to put the question up here using the left endpoint to find the Riemann sum for 2 to the x, from x equals 1 to x equals 3. And I want you to use 5 as your choice of n, 5 subintervals. Go ahead and pause the video here and work through that and see if you can get an answer that you like. Alright, here's what I get when I work this out. Your delta x is going to be 0.4 because your width of your interval, 3 minus 1, gives you 2, and then you're dividing that by 5, your choice of n, which gives you the 0.4. For each of your subintervals then, you're starting at 1 and adding 0.4 each time to create each of these. You'll find your left endpoint, you'll run it through the function, you'll get some just lovely values. And you'll find the area, right? Base times height. The base for each one is 0.4. and you'll be multiplying that by the height, so 0.4 times 2 is 0.8. 0.4 times 2 blah, 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 is blah, 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 and so on. Adding all these up gives you an area of about 7.51. Not bad. Not bad at all. Now, you might look at this and be like, well, that's honestly awful. Yeah, I mean, kinda, yeah. But no part of this was hard. It was just tedious. The process of going through and working out, okay, well, I got the width of each one. Now I'm starting at 1. I gotta add 0.4 to get to each next number that I'm going to be using here. And then I gotta find 2 to that number. Like, okay, yeah, it looks a little gross. But it's not hard. It just takes a little while. But doing it for 5 rectangles, yeah, it's not so bad. You want to do it for 10 or 20? That gets under your skin just a little bit more. But that's the thing, right? That's where we're going. That's what we had talked about before. The whole idea here is more rectangles means more accuracy. And if I want the area under the curve, that's ultimately what we're going to have to do. The Riemann sums can get us some nice approximations, but calculus is not always about good approximations. Sometimes we want an exact number. And this is one of those times, right? When we found derivatives, it wasn't just about, finding something close to an instantaneous rate of change. I wanted the instantaneous rate of change. I want to know how fast we're going right now. I want the slope of the tangent line, not a secant line that's pretty close. This is one of those times when we want to be exact. And this is where that limiting process is coming back. That is the whole spirit of the limiting process. We did it with differentiation, and now we're doing it again with integration. With a Riemann sum, we're cramming some rectangles under the curve and using that to approximate the area. But of course, with 4 rectangles, it doesn't look great. There's a lot of big gaps. There's some overlap. There's some underlap. It doesn't look like a true approximation of the area. No problem, we cram a few more under there. You put 20 rectangles under the curve and it looks a bit better. Those gaps shrink right down. The overlap is a little bit smaller. The underlap is a little bit smaller. It's a little bit better overall. And if you keep going, it gets better and better. You put 100 rectangles under there, and man, it's starting to look really good. It's starting to really look like the area under the curve. It's still not perfect though. It's still not exact. And the spirit of calculus is to say, what if I kept going? What if I kept doing this more and more forever? What if I just kept cramming rectangles under there forever? Arbitrarily many. What if every time I put rectangles under there, I put one more? We're asking the question now from the limit perspective. If I were to do that, would this approach anything? Would it be getting closer and closer to something? We saw what happened with 4 and 8 and 20 and 100. Well, what happens with 200, 1,000, 1,000,000, 1,000,000,000? Is it going somewhere? Can I tell that if I could keep doing this for the rest of eternity, what value would I be getting close to? Because that value is the true area under the curve. How do I find that? Well, the way you find it with anything in calculus, the limit. Limits are the fundamental piece of all of calculus. It's why we start with them, because everything relies on that idea. Everything in calculus is about, what am I getting close to? What am I approaching? What would happen if I kept doing this forever? So let's have another look at this question. Our same f of x equals x squared plus 1. And let's see if we can use our Riemann sums to find the actual true area under the curve. How would we do that? Here's how. Let's have a look at this question. This is actually the same one that we did earlier. Evaluate this definite integral from 0 to 4 of x squared plus 1 dx. In other words, find the area under the curve of x squared plus 1 between x equals 0 and x equals 4. Except now we want to find the actual area under the curve. We did this with a Riemann sum. We did it with 4 rectangles and with 8 rectangles. Now we want to expand that and see if we can use this idea of a Riemann sum to get us the actual area under the curve. How do we do that? Well, here's how. Step 1, choose a method. And by that I mean if we're taking a Riemann sum, then we need to talk about which point in the interval we're going to send up to the curve. We could go by left endpoint, or right endpoint, or midpoint, or random point. There's lots of great options. But mainly those 4. And I know that your gut says that you want to go with the left endpoint, but I might surprise you a little bit. I'm going to go with the right endpoint. I think that's actually going to work out a little bit nicer. Don't freak out. Trust me on this. Just trust me. Number 2. Set up a Riemann sum for an arbitrary number of subintervals. In other words, I don't want to decide ahead of time that I've got 4 rectangles or 8 rectangles or 20 or 100. I want to leave it open and arbitrary. I want to just give it a name like n. Let's just say that there's n rectangles. What would my Riemann sum look like then? Well, the definition of a Riemann sum is that it's going to be the summation from 1 to n of the height of each rectangle, f of c sub I, times the width of each rectangle, the delta x sub I. If we're going to set up this Riemann sum, we should talk about what that will look like for us in this specific example of our function x squared plus 1. Let's start with that delta x sub I. In all the examples that we've done, our widths didn't change. Every rectangle had the same width. They were, when we had n equals 4, they were all 1 unit wide. When n equals 8, they were all 1/2 unit wide. And we want to keep that the same. There's no reason to deviate from that. So instead of calling this delta x sub I, I'm just going to call it delta x. It's not something that will change for every value of I. They're all going to be the same. But what is it? What will it be? Well, we figured that out too, because for each one we said it was b minus a over n. And while I haven't pre-decided each choice of n, b and a haven't changed. It's still between 0 and 4. That part isn't arbitrary. That was part of the question. So I still know the width of my interval. It's still 4 minus 0, which is 4. And that delta x is just going to be the more arbitrary 4 over n. They're all the same width each time, but I can't tell you exactly what that width is unless I pre-decide a choice of how many rectangles n. So that's my delta x. But what about this f of c sub I? Well, remember that this f of c sub I, this business that we're doing here, this is representing the height, right? This was the width, and this is the height. This is the part that we're sending up to the function to find out how tall my rectangle is. The f of is representing the sending it up there. The c sub I is just the point in the interval that we're sending up. Right? Which point am I picking to send up to the function and determine its height? Well, I decided that I was going to go by the right endpoint. So what would that look like? Well, let's talk about that for a moment. Because in the previous examples that we've done, when we had like n equals 4, we worked out our delta x and said, well, delta x had to be 1, the width of each rectangle was 1. But then we found all of these points that we plugged into the function that we ran through. If I wanted to find the points, the right endpoints of each interval, I would say, well, I'm starting at 0. I need to get to the right endpoint of that first interval, which means I need to add the width of that rectangle, which is 1. Plus 1 over here to get me to this 1. And that would be my first one, right? That's be the first point that I would send up. I would send a 1 up to the curve and see what that value is. For I equals 1, that's the choice of C. My c sub I would also be 1. What about when I equals 2? For my second rectangle, I would need to go another 1 over here to 2. And I would send 2 up to the curve and see how tall it would be. When I equals 3, I would go another 1 and send in 3. When I equals 4, I would go another 1 and I would send in 4. And these would be my 4 choices. And they're not hard to find. I got them just by starting at the left spot of my interval and then just adding the width of a rectangle each time. Same goes for when n equals 8 too, right? My delta x in that case is 1/2, and we went by midpoint when we did it in class, but if you went by right endpoint, same business. I'd start at 0 and say my next interval will start 1/2 later at 1/2. And the one after that will start 1/2 later at 1, and then 1/2 later after that to 3/2, and so on, so that I can say that my value of c sub I, in general, if you want to know what that right endpoint is going to be for the ith rectangle, well, the way you would find it would be to say start at 0 and add the width of your rectangle I times. If I want to know what point I'm going to be using for my third rectangle, I would start at 0 and say, okay, well, let's find the width of 3 rectangles. 1, 2, 3. Oh, it would be at 3/2. And that would be my process no matter what my function was, no matter what my choice of n was. I would say start at that left spot, in this case 0, and then add to it 1/2 times I. I add the width of each rectangle that many times, and that tells you what the right endpoint is for the ith rectangle. Now here that was 1/2 because that was the width of my rectangles, but in general, this would be my process. I would start at the left endpoint of my interval, a, and then add to it delta x times I to find that right endpoint. Here we even know our delta x and our a, and my left endpoint is 0, that's where we're starting, and my delta x is this still arbitrary 4/n times I. Well, if that's my value of c sub I, then that's what I would be plugging into my function. So for our specific setup then, that's what our c sub I looks like. It's 4/n times I. Those are the right endpoints that I'll be plugging in for all of my choices of I. Now, one thing I want to point out in this expression that we have is that I is changing as we go through the values. That's the way that the summation was set up. I'm looking at what this will look like when I equals 1, when I equals 2, when I equals 3, and so on. But n is fixed. It's arbitrary, it's unknown, I don't have a specific value for it, but it's not changing, not inside the summation. I is the only thing that changes inside the summation. What we're designing here is essentially a formula for what we would get from a Riemann sum once you give me a value of n, so that when we're done, we could say, hey, if you chose n equals 4, here's what you'd get. If you chose n equals 1,000, here's what you'd get. The value of n is meant to be fixed, it's just unknown. But that means that it's constant here. I is the only variable within inside the summation. So this 4/n, I may not know its value, but it's still a constant. And if it's constant, then I might as well pull it out to the front of the summation. I've got that nice summation rule that lets me split summations up over sums and pull out scalar multiples. I kind of like the idea of doing that because now I can focus more on simplifying this, find this summation, and then deal with the 4/n later. Which brings me to our third part of this process, simplify, since we know what the function is. I do know what the function is. My function is f of x equals x squared plus 1. So I know what this expression should become. I'm plugging in 4/n times I for all of my values of I, but I can just take that and plug it into the function. Everywhere I see x, I'll write 4i/n. And if I plug in 4i/n everywhere I see x, I'll get 4i/n squared plus 1. And I can simplify that. Everything that's in here is a product, so I can apply my exponent to each piece of it. 4 squared is 16, n squared is n squared, and I squared is I squared. And then I'll have a plus 1, and I'm supposed to be doing this for every value of I. This is the summation that I have to work with now. Okay, I was able to simplify based on my knowledge of the function. I can actually simplify this a little bit further, thanks to my knowledge of summations. we can use the properties of summations to simplify this even more. Remember, I'm allowed to split a summation up over a sum. So if I've got this sum in here with this plus 1, I can break this up into two pieces and say, let me find this massive summation for all of this, plus find the summation for just this one. I can break it up over those pieces and find those two individual sums. Gets even better, because this now is another constant that I can pull out and say that the only thing that's changing in here is I squared, so let me pull that 16 over n squared out of this summation so I can just do this one. And this summation from 1 to n, we actually talked about that one. That was one of the 4 summations that we did in class. We talked about when this is 1i squared, and I cubed. We all have formulas for all of those. And the one for 1 is the best of all. It's just n. So now I've taken this huge summation and whittled it down to this one summation of just I equals 1 to n for I squared. Everything else was constants that I was able to pull out, move around, break out, which takes me to this last summation, and yeah, I've got a formula for that one too. Before I use that formula for I equals 1 to n of I squared, I'm gonna clean this up a little bit. I'm gonna go ahead and I'm gonna distribute my 4 over n here. 4 times 16 is 64, n times n squared is n cubed, 4 over n times n is 4. That makes things look a little bit better here. Now I can focus more on this last summation, I equals 1 to n of I squared, and I've got a formula for that one too. We said that one always works out to be n times n plus 1 times 2n plus 1 all over 6. It's just one of our formulas. We know that that's going to work out to be this. No matter what the value of n is, that's what that ends up being. And notice how huge this is. I mean, not physically, although it is pretty big. That's on my screen. That's probably a good, foot long. But it's huge in the sense that we got rid of summations. We were able to turn this into a formula where no matter what the value of n is, I can tell you what the Riemann sum would be for that many rectangles. It's just a plug and chug at this point. If you were to plug 4 into this, you would get the same value that we got when we plugged in 4, which I think was 18. If you were to plug 8 into this, you would get the same value we got when we plugged in 8, 25.25. Whatever the value of n is that you want to find out what the Riemann sum would be, you can just plug it in and you never have to take a single summation. We found a formula. And we'd like to clean it up a little bit and simplifies a little bit. I mean, for starters, for this term, I got 2 terms here, right? All of this and 4. And in this term, I've got n times the entire top and an n times the entire bottom. So those will cancel. And turn this into just n plus 1 to n plus 1 all over n squared. I also get a 2 to cancel from the top and bottom. 2 goes into 64 and 2 goes into 6. So I can simplify that expression a little bit. I guess I could do it even more, right? I could expand n plus 1 times 2n plus 1 into 2n squared plus 3n plus 1. And now I guess when I put it all together, multiply straight across for my fractions, take 32 times all these, take n squared times 3, I get this massive fraction that I have at my disposal right now. Maybe a little bit of a cleaner formula here, debatable I suppose, but definitely one that is very much plug and chug. You could still plug in your choice of n to see what the Riemann sum should be. Now comes the calculus. Take a limit. All of this was leading up to this idea of cramming more and more rectangles under the curve to get that exact value. Where is this going? I can find out what the Riemann sum is for n equals 4 or 10 or 100 or 1,000. I can do that. But I want to know what its approaching? What is it getting close to? As n gets bigger and bigger and bigger, does this get closer to something? And that's just straight up a limit as n goes to infinity. You might recall from Calc 1 that if you're taking a limit as n goes to infinity, if the degree of the top is the same as the degree of the bottom, then you ultimately just take the ratio of those leading coefficients. Nothing else actually matters. So this whole fraction is just going to be 64 thirds. And 64 thirds plus 4 is 76 thirds. That is the actual area under the curve, that 25.33 repeating, and so on, that we saw before. Now, I know that was a pretty intense process. Feel free to look back through it and check all the math and make sure that you can follow everything that we did there, but hopefully you kept with me and it didn't put you to sleep. But that's our general process. That's how we do it. It's really that way every time. The only things that would change would be what function am I using. That time it was x squared plus 1. And what are my endpoints? That time it was between 0 and 4. But that idea is kind of always there of I know how I would choose my delta x, and I know how I would find what that c sub I is. Then there's just a matter of running it through the function and simplifying, using what I know the rule of the function to be and what I know about summations, being able to pull out constants, things that just have n in them, and then working that out, hopefully having a summation rule that lets me simplify it to something that just has n so that I can take a limit. All of that we could summarize in this theorem that I have restated to be simpler, using the choices that we would likely make each time. Here's that theorem. For a function f continuous on a closed interval a to b, it does need to be continuous for this to work, let delta x equal b minus a over n. With that choice, then we can say that the definite integral from a to b of f of x dx is what we just did. That limit as n goes to infinity of that sum from 1 to n of our f of c sub I, in other words, the a plus I times delta x times delta x. It looks very mathy, but this is kind of a summarization of everything that we just did, all in one cute, very mathy looking line. I want to do one more example with you that's got a little bit more meat and potatoes, but it's not too bad. And hopefully you'll see from this that it's kind of the same process pretty much every time. Let's have a look. Let's find the definite integral from 1 to 11 of x squared minus 5x plus 2 dx using Riemann sums. Same process. I'm gonna keep with that right endpoint and have my delta x be the width of the interval. That's 11 minus 1 is 10 over this n that is going to stay arbitrary, so my delta x is 10 over n. That means this, if you want to go straight for this formula, we could write it like this, right? And say that this will be, I know I'm going to be taking a limit, I know I'm going to be working with a summation, and this inside piece, my c sub I, is always going to be that a plus I times delta x. My a is 1, the starting position here of this integral. My delta x we just worked out to be 10 over n. So I kind of got everything that I need in a sense. It's just a matter of writing it out and simplifying. I know what every piece is supposed to be. I got to take this 1 plus 10i over n and run it through this function of x squared minus 5x plus 2, and that does get pretty gross. Take a moment just to confirm that this is exactly what's happening here. First of all, let me switch this over to a pointer. My 10 over n is still constant, so I'm pulling that out to the front. That's where this comes from. The rest of this is coming from taking this inside, the input, and running it through the function. 1 plus 10i over n squared, that's this, minus 5 times my input, 1 plus 10i over n, that's here, minus 5 times all that, plus 2, okay, right there, and there we go. This part came out, this part stays in, and this part is disgusting, but here we are. As far as simplifying this goes, well, the main pieces would be I need to distribute this -5, and I'll need to square this out, which is a lot more unpleasant in this example than it was in the previous one, because in the previous one I had a 0 here, so I got to just apply that square. I can't distribute an exponent over a sum, so I'll have to actually FOIL this out. 1 plus 10i over n times 1 plus 10i over n. Although I typically use the shortcut of square the first, square the last, multiply the two together and double it, just like you'll get if you FOIL it out by hand. So that's square the first, 1, multiply the two together and double it, 1 times 10i over n is 10i over n, doubled is 20 over I over n, plus square the last, that's 100i squared over n squared. Distributing my -5 gives me -5 minus 50i over n. My goodness, this sucks over video. I'm so sorry. Here we are. Plus 2. Simplifying this. Once we get through this, hey, we're just waiting. We're just trading through muddy math, right? But it's just algebra from this point. What can I do with this? I can break this up into individual sums, but I should probably combine like terms first, right? 1 minus 5 is -4, plus 2 is -2. 20i over n minus 50i over n is -30i over n, and nothing combines with this, so I'll have that 100i squared over n squared. Now I can break that up into all of these different summations and pull out the constants, right? When I break it up into these 3 separate pieces, from this one I'll have this constant of 100 over n squared that I can pull out. From this one I'll have this constant of 30 over n that I'll get to pull out. And from here I guess I could think of it as pulling out a -2 and calling it just 1. I like writing it that way because it makes each one of these summations look exactly like the summations that I have a direct formula for. We talked about the summations of 1, I, and I squared, and I cubed, which thankfully didn't show up here because that could have been really annoying. The worst in some ways is, well, maybe not, depends on what feels like the worst part of this to you, I guess. Pulling this 10 over n out I think really helps. Pulling out my individual constants definitely helps, but now I need to actually apply those formulas. Before I apply the formulas for these summations, I'm actually going to distribute my 10 over n, because having this kind of double, thing going on where I'm about to replace these with parentheses, and having all kinds of parentheses floating around makes it look way worse than it actually is. So I'm going to distribute this to each piece. 10 times 100 is 1,000, n times n squared is n cubed, 10 times 30 is 300 now over n squared, and here I'll get 20 over n. So now I don't have this hanging around out front, I just got constants in front of each one, which was unavoidable. But now I can apply those formulas that we know. The summation for 1 is just n. The summation for I, we said, is n times n plus 1 over 2. And the summation for I squared was n times n plus 1 times 2n plus 1 over 6. We've applied the formula, so now it's going to be a matter of simplifying this. You can do however you like. I do get some nice cancellations. The n and the n cubed, and the n and the n squared, the n and the n all go away, one after the other. And I'm still gonna have to expand these out. I don't think there's any way around that. Since I'm taking a limit as n goes to infinity, having them as full expanded polynomials is actually helpful to me. So I it all over one fraction though, because I'm still allowed to split a limit up over a sum or difference. And so I can just do that 3 times here, saying, okay, I've got the same degree on the top and bottom, so I'll have the ratio of the leading coefficients, 1000 over 3. I'll have negative 150 over 1, and of course I'll still have negative 20. And I put all of these together. people could wiggle their ears. That's 46 out of 200 is 23%. Hey, that's more than 20%, right? Case closed. Right? Well, no. It's not case closed. It's possible that fewer than 20% of Americans can wiggle their ears. I know, right? But I just happen to get lucky. And just happen to get a group of people where 23% could do it just by luck, just by random chance. How do I know that that's not the case? Or what would lead me to believe that that's not the case? How can I have confidence that that 23% wasn't just luck? There's actually a great answer to that. We want to know if we got lucky. We want to know, what are the chances, if I'm wrong, if the population only has 20% of its people able to wiggle their ears, what are the chances that I would just happen to get a group where 23% could do it? Well, we can answer that question by doing a little bit of experimental probability, a little bit of what they call empirical probability. Here's what I'll do. I'll imagine that I've got a population of however big you want, and let's say that I know that 20% of the population can wiggle their ears. Exactly 20%. Here's what I'll do. I'll look at this fictitious population, and I'll sample my 200 people from it. This isn't 200, but play along. I'll look at my sample of 200, and I'll look at, okay, what percent of them were able to wiggle their ears? And I'll keep track of it, and I'll do this over and over and over again, with the hopes of discovering, hey, when I have a population with 20% able to do it, how often, when I take 200 people out of it, how often do I end up with at least 23% able to wiggle their ears? Here's a little applet that I've used when I've taught an Intro to Statistics course that I really like. It lets you simulate this kind of thing. Here I've created a fictitious population where 20% can wiggle their ears. I'm going to take a sample of 200 people from that, and I'm just going to do it one time, and I'll see what I get. Let me draw some samples here. What do we got? From this first one, when I drew 200 people from this population, 37 of them were able to wiggle their ears, and 163 could not. Okay, I'll make a note of it down here. Okay, that time, when I tried it that time, only whatever percent that is, 37 over 200. And now we'll do it again. All right, what do we got? Okay, this time, 49 were able to do it this time. A little bit better, a little bit more up there. What if I do it again and again? And again and again and again and again and again. And the whole idea here is that I keep doing this over and over and over a lot of times. And I want to do it like 10,000 times. And say, when I do this 10,000 times, what happens? How often do I get at least 23% able to do it? Well, if I've done it 10,000 times, I can ask the computer to keep track of that. Hey, how often out of the 10,000 times that I simulated taking this survey, how many of those 10,000 times, what percent of those 10,000 times resulted in me getting at least 23%? In this case, it looks like that happened 16.81% of the time. Now that seems to suggest that if only 20% of the population can actually wiggle their ears, if it's exactly 20%, then the chances, the probability that I would get a group where 23% could do it just by luck is around 16.81%. There's about an almost 17% chance that I could get that by luck. But what if I couldn't simulate it? What if I couldn't just check and see what the chances are of me getting what I got by luck? And until recently, computers weren't powerful enough to do that kind of thing. And maybe my simulation isn't that great anyway, right? I only got 200 people out of the United States of America. It feels like I could probably do a little bit better than that. What if I can't simulate my answer? Or what if I want it to be a little bit more precise? Well, we have an answer to that too, and it's beautiful. As long as my sample size is decently large, and by decently large I mean at least 20, mine is 200, as long as my sample size is decently large, I actually know in general how my data is going to be distributed. I know what this shape is kind of going to look like. It's what we call a normal distribution, this bell curve shape. And thanks to mathematicians of yore, I have a formula for that. I actually have a function where I know what that's going to look like. The formula for the normal distribution looks like this, which it's got a lot going on. Pi is pi, as you've seen it. Mu is the average value, the center of all of my data. And sigma is the standard deviation, how spread out is my data. Given everything that we know, I can actually estimate what that value of sigma would be in our circumstances, which is about this value. So for this situation, this would be the formula for the normal distribution that I would get if I were to simulate. I would get a curve that looks like that one. And just like before, when we wanted to simulate and see, well, how much of the time is it at least 23%? When I simulated, I wanted to know how many out of my 10,000 times were at least 23%. But if I can't simulate, if all I've got is this curve and I know what the curve looks like, I can answer that same question by trying to figure out how much area is under the curve. One of the things about probability distributions is that the area underneath them forever is 1. Always. And so finding the area under the curve would essentially give me what percent of the time would I get something that's at least 23%. But the area under the curve that's at least 23%, well, that's the definite integral. In this case from 0.23 to infinity of f of x, and we haven't really talked about that scenario, but we will. I want that area under the curve. It'll give me an idea of how likely this is. And in this case, if you work out the area under the curve, it works out to be about 14.44%. Oh, by the way, in probability, we set the bar pretty high, and it has to be a really low chance that I could get what I got by luck. We draw the line at 5%. If there's even a 5% chance that you could get what you got by luck, then you can't conclude anything really. There's nothing there. In our case, having a 14% chance that I could have gotten that by luck means that's on the table. I could have gotten that by luck. I cannot conclude that more than 20% can wiggle their ears. It's still a possibility that I got lucky. If that feels high, swing by my office. We can talk about that. There's a reason that we keep it so low in statistics. I know that some of this may have gone pretty fast, but feel free to look at it again, slow it down, or come talk to me in my office and we can go through things in a little bit more detail. But I wanted you to get a picture, at least a little bit, of how this can be useful. And it's useful in a lot of different ways. It comes up in probability, but it also comes up for engineering, and it comes up in a host of other applications where area under the curve is often in itself, having area and volume, a thing that I want to know, or it could be representative of some other concept that's connected to it. Practice some Riemann sums, see how it goes, and see how it feels getting that area using that limiting process. It's the next big thing for us in calculus, using a limit to find the area under the curve. There's more to say about it though, and that's what we'll talk about on Thursday. I'll see you then. You can be here, but you can't do any whooping, okay? Do you agree? Take that as agree. Every time I touch my leg, this happens. I should stop doing that. I'm mostly just getting the ganache right now, but there is a little bit of coffee, and I gotta kind of like the balance.
That's not enough to conclude that it's always true, or that it's true for all. You're already whooping at me. You've only been here like 3 minutes. Which is appropriate because, a tiramisu, guys. No, I'm gonna edit that one out. Can you wiggle your ears? I'm still rolling, aren't I? Well, no. Not case, because I know. It's a shock.